Good afternoon, and I welcome you all to this lecture session of the course Laws of Thermodynamics. Now, last class we discussed the Kelvin Planck statement and quasi statement, two formal statements of second law of thermodynamics from the perspective of mechanical engineering, and we have shown that the equivalence of the two statements, that means if one statement is invalid, then other statement is automatically invalid, and we have shown this in the case that Kelvin Planck statement is invalid. If we consider, then we have seen that the quasi statement is also invalid, and vice versa. The other one is left to you as an exercise, or you can see in any book. Now, today we will start a very important concept which is known as reversible process. What is a reversible process by definition? Initially it told you the directional constant that some processes are unidirectional in nature, they cannot be brought back in the other way, they cannot be made to occur in another way, That means it occurs only in one way, not the reverse one. The reverse one takes place. Apparently it means those processes which by its just definition, English mean is reversible. That means the process which can take place in both the ways, and the process which cannot take place in both the ways, that means which takes place in one way or one direction, that is irreversible process. No, that is not the correct. I told you earlier that there is some permanent change in the surroundings when a process takes place, a system from initial state to final state, and the reverse of the process, that means from the final state to initial state, there is some change in the permanent change in the surrounding, and that gives rise to the concept of a reversible process. You understand? So, therefore, reversible process by its formal statement you can tell like that. A reversible process is that process if at the conclusion of the process performed by a system going from one state, initial state to the another final state, the process is reversed back, okay, so that this system is brought back to its initial state. The surrounding cannot come to the initial state, or the initial state. Surrounding cannot come to the initial state. This is for all natural processes. If we can conceive a process which after its conclusion from one state to other state is brought back in the reverse way to come to the initial position, and surroundings also comes to the initial position, that process is known as reversible process. That means we can restore both the system and surrounding at their initial condition or initial state by occurring the process, by making the process to occur in one direction from one state to other state, and reverse back from the final state to initial state in such a way that surrounding does not suffer any permanent change. That means surrounding also comes to its initial state. That process is known as reversible process. But unfortunately, all processes in nature are not reversible. They are all irreversible process. Now, I tell you one example which I told earlier, that with respect to heat transfer process, you see that if we consider heat transfer, natural case heat transfer, T1 to T2, where T2 is less than T1, heat transfer takes place. But the reverse is not possible. That means this is a natural process which occurs in one direction. This way it is reversible. But if we consider this one, that a body, let us consider at a temperature T1, let 20 degrees Celsius, for better understanding, is heated, a finite body, to a temperature of 80 degrees Celsius. This is heating. And if it is cold again, cooling from 80 degrees Celsius to 20 degrees Celsius, system comes back to its initial state. That means this process of heating is not a unidirectional process, the cooling is also possible. But how does system surrounding gets a permanent change? Surrounding cannot come to the initial state. Let us consider this, that to heat it from 20 degree to 80 degree Celsius, we have to keep it in contact with a hot body, TH, whose temperature should be either 80 degrees Celsius or greater than 80 degrees Celsius. If you keep it at 80 degrees Celsius, then heat transfer at the end will be very slow. When the temperature will be close to 80 degrees Celsius, the rate of heat transfer will be slow because of infinite small temperature difference. So therefore, for a natural process to occur within a finite time, we take this TH greater than 80 degree, let 100 degrees Celsius, and they are put into contact, thermal contact by a diathermic wall. Then it takes heat, okay, and goes to 80 degree. When this 80 degree Celsius body is cooled, that means the reverse process to bring it back to 20 degree Celsius, we take a body, let's take this TL, lower temperature body, which is equal to 10 degrees Celsius, and it gives heat, takes heat from the body and cool it to 20 degrees Celsius. Then you see, though the system attains its initial state, but surrounding, what has happened? The surrounding has given heat from its source at 100 degrees Celsius, that means from its thermal reservoir at 100 degrees Celsius, and he has got the heat back to his thermal reservoir at 10 degrees Celsius. And this way, surrounding is not at the identical condition which it had initially. No, it has given heat from one part of the surrounding, one reservoir, and has taken it in another reservoir. So if you want to make the surrounding to the initial state, that means to restore this surrounding to its initial state, then we have to give back this heat where from it was given. This was the surrounding, and this is another part of the surrounding. The two together defines the surrounding. That if we can give this heat to this body, then surrounding will come to the initial state. But this is not possible. This violates the Clausius statement. Without any other external aid, we cannot do it. We can do it by the help of a heat pump or refrigerator. There we have to take work. That means surrounding suffers a final change. So therefore, this way surrounding suffers a permanent change. Similar way, I tell you that if you have a cylinder and piston, then if you compress a air from some pressure and temperature to a high pressure and temperature, and then expand it, and if you come back to the initial state after compression then expansion, then the compression process is an irreversible process. Why? Or other way, if first expansion then compression, so that expansion followed by compression or compression followed by expansion, so that the initial state is restored. But in that case also surrounding suffers a permanent change, that in actual case the work delivered in case of expansion and work required or given in case of compression are not same. This is because of mechanical hysteresis due to friction and other dissipative effects. So therefore, this way all natural processes, when they come back, when the natural processes, when a system changes from one state to other state, is made to occur in the reverse way for the system to restore its initial position, initial state rather, then the surrounding suffers a permanent change. The surrounding state is permanently changed. So this way we define that all the natural processes are irreversible. If we can make the process reversible, then this is possible, because the definition of reversible process is that after the conclusion of a process, if it is reversed back, both the system and surrounding can be restored to its initial state. But this never happens. That I will show you. That causes. Now why it does not happen? Happens. Causes, so therefore we must know causes of irreversibility. All natural processes are irreversible process. Irreversibility. Causes of irreversibility. Now causes of irreversibility. All natural processes are irreversible process. Processes are irreversible. Now this causes of irreversibility here is the lack of thermodynamic equilibrium. You have already come to know what is thermodynamic equilibrium. Lack of thermodynamic equilibrium. Lack of thermodynamic equilibrium. And this thermodynamic equilibrium consists of mechanical equilibrium. So therefore, lack of mechanical equilibrium, lack of mechanical equilibrium, lack of thermal equilibrium, lack of thermal equilibrium. Three equilibrium consists the thermodynamic equilibrium that you have already read. We have discussed it earlier, and lack of chemical equilibrium. Equilibrium. Now, lack of mechanical equilibrium happens when delta P not equals to 0. In case of mechanical equilibrium, delta P is 0. There is no pressure difference between the system and the surrounding. And the mechanical work is delivered in that way that there is no disbalance force acting on the system. So delta P has to be 0 for mechanical equilibrium to be achieved. But delta P not 0 is the lack of mechanical equilibrium, departure from mechanical equilibrium. Similarly, the thermal equilibrium demands delta T should be 0, but delta T not 0 is the lack of thermal equilibrium, by virtue of which the system transferred heat to the surrounding, by virtue of which system transfers work, that means interacts work with the surrounding, interacts in terms of heat transfer with the surrounding. Similarly, lack of chemical equilibrium is concentration difference is not 0, or chemical potential, which is responsible for chemical reaction, this is responsible for mass transfer, they are not 0. But if all delta P, delta T, delta C, delta mu are 0, the system is in thermodynamic equilibrium, doesn't interact with the surrounding in terms of either work transfer, heat transfer, mass transfer, or chemical reaction. So therefore, for a reversible process, this has to be 0. So these are the causes of irreversibility when they depart from their 0 value. There has to be some pressure difference, there has to be some temperature difference, there has to be some del C, del mu for irreversibility to be there, for the existence of the irreversibility. So one is lack of thermodynamic equilibrium, another is the dissipative effect. Dissipative effects. Dissipative effects. Dissipative effects are like this. Under this heading, dissipative effects, we have mechanical friction, we have mechanical friction, you know these are the dissipative effect, fluid viscosity, these are inevitable in practice, fluid viscosity, inelasticity, then magnetic hysteresis, electrical resistivity, electrical resistance. All these things are dissipative effect, and in any process, for example, in mechanical movement of piston and cylinder, there is mechanical friction. Fluid flow, fluid viscosity appears, inelasticity, if you stretch a wire, magnetic hysteresis, in magnetic work transfer, in electric resistance, electric work transfer. And the effect, these all dissipative effects, basic purpose is same. What they do, they convert the mechanical energy or the work, mechanical work, electrical work, all constitutes the work in thermodynamics into intermolecular energy, by which the system becomes hot. So therefore, this is known as dissipative effect. They dissipate the energy, and why the term dissipation is there, I will tell you afterwards, that mechanical energy or work, they are organized form of work and energy from the molecular point of view, where the intermolecular energy is disorganized form of energy, and these are called as low grade energy, that is high grade energy. And already we have seen earlier that heat cannot be converted completely into the work, but work can be converted completely into the heat in a heat pump or refrigerator. So that is another way we define high grade and low grade energy. That means work or mechanical energy is high grade energy which is being transferred to the intermolecular energy by all these agents. They are the agents and they are always present in any process and they are known as dissipative effects. So this way we see that the thermodynamic equilibrium is distorted and the dissipative effects altogether makes this system process irreversible. Now what happened? That means irreversibility, if you have to have a reversible process, purely reversible process, then this has to be 0. Delta P is 0, delta T is 0, del C 0, that means there is no process at all because they are the motive forces for the process and obviously there will be no dissipative effects. That means if you occur if any process is occurred, if you make to occur any process, then automatically there will be lack of thermodynamic equilibrium. Therefore, this statement is very important. The irreversibility of any natural process lies in its basic requirement for the process to occur. Irreversibility of any natural process lies in its basic requirement for the process to occur. So therefore, without any, if there is no process without any lack of equilibrium, that means for complete thermodynamic equilibrium, system is at rest and there will be no dissipative effect. So therefore, pure reversible process, actual reversible process, pure reversible process can never occur. But we can think of some process which is close to reversible process. What are those? Let me see. Close to reversible process. So from this concept, we can think of process close to reversible process. Why? If we have a process where thermodynamic equilibrium departure is infinite small, that means for any process where delta P tends to 0 is very small, delta T tends to 0, very small, delta C tends to 0, delta mu tends to 0, and dissipative effects tends to 0. Now when this will tend to 0, the process will be extremely slow. Heat transfer under infinite small temperature difference is extremely slow. Work transfer under an infinite small pressure difference, mass transfer under infinite small concentration difference, chemical reaction under infinite small chemical potential difference are extremely slow and obviously dissipative effects will tend to 0. This process is known as quasi reversible or quasi static process. And another condition is that when this process will take place under a very small, that means when the process takes place in such a way that there is an infinite small thermodynamic potential, thermodynamic equilibrium, or there is an infinite small departure from thermodynamic equilibrium and process is extremely slow and each and every state the process is in thermodynamic equilibrium. That means, for example, if we expand a gas with a very small delta P from a high pressure to low pressure, first you expand from a high pressure to a very small delta P difference, very close to the high pressure, then we keep the gas at rest for some time, wait, so that it comes to thermal equilibrium. Then again we expand to another lower pressure which is very close to the initial pressure, very slowly, and then at rest for some time so that it attains a thermodynamic equilibrium. That means the process should pass through all thermodynamic equilibrium states and is extremely slow and takes place under infinite small potential difference, either delta P, delta T, delta C, delta mu. This is like that. If I work like that, it is an irreversible process. But if I work like this, that's slowly and take rest for some time, thermodynamic equilibrium exists within me. Thermodynamic equilibrium exists. So this is a reversible process. But reversible process is extremely slow, so that from one state to other state, from one state to other state, a system takes infinite time. So this is known as quasi-reversible process. Now this can be explained in terms of the heat transfer. Let us explain that there is a T1 temperature, if we have to make, it is a thermal reservoir source. If you have to make a reversible heat transfer to a body, then this body temperature should be T1 minus dt. Small difference where dt is extremely small. That means infinite small temperature difference heat transfer is the reversible heat transfer. Or you can take that some T2, T2 plus, other way you can show that heat is transferred from a body at T2 to T2 plus dt. That means the heat has to be transferred to an infinite small temperature difference. Now, we earlier considered that a 80 degree Celsius, 20 degree Celsius body was heated to 80 degree Celsius. And what we did? We first took it a body of 100 degree Celsius, which is more than 80 degree to 20 degree, so that in a finite time it is heated to 80 degree Celsius. That is heating process. And similarly, if you cool, we place a body at 10 degree Celsius and allow the heat to flow from here, and it will come in a finite time 20 degrees. This is an irreversible process you have seen, because the surrounding doesn't come to its initial state after cooling. But now if we make a reversible heat transfer, this is a reversible heat transfer, but here the bodies are at same temperature, T1, T1 minus delta T, T2, they are the thermal reservoirs, source and sink, finite heat capacity, infinite heat capacity. But here the bodies of finite heat capacity, heating process, that 20 to 80 degree. In that case, we can achieve the reversible heat transfer if we consider a number of reservoirs with a very small difference, 0.01 degree Celsius, 20, 20.01, 20.02, 20.03, like that in infinite number of reservoirs, like 79.01 difference, 99, then last two is like that, 80 degrees Celsius. Okay. So if you consider this infinite number of reservoirs with 0.01 degrees Celsius difference, that we just take arbitrarily, and finally to 80 degree, and you first make this system to come to this contact, so that it will be heated extremely slowly with a temperature difference of 0.01 degree Celsius. That means which is a limiting reversible process or quasi-reversible process, a limiting case, quasi-static process, because the process is extremely slow. When it reaches 20.01, then you wait for some time so that the entire system assumes a uniform temperature of 20.01. Then you keep it in contact with 20.02 reservoir. It is heated. That means I am doing a wrong. So it is heat is going so that it is heated to 20.02. Then you bring this here 20 point. When it reaches 20.02, we bring it here. So that always what we do, 20 to 20.01, take some time so that it reaches uniform temperature. Then with the reservoir at 20.02, then it reaches 20.02 with the reservoir at 20.03, so that it gets 20.03, and finally it gets 80 degree from this 79.9, then 80 degree. Okay, that means here the body will attain 79.9 degrees Celsius, then it is 80 degrees Celsius, which means that always the heat transfer takes place with an infinite small temperature difference. It's not that initially I put 100 degrees Celsius, huge temperature difference. Initially temperature difference is very large, irreversibility is very high. Finally it goes down, but still when it goes to 80 degrees, still there is an irreversibility, because the heat transfer takes place with a temperature difference of 20 degrees. But here always heat transfer takes place with a very infinite small temperature. If you can reduce it to 0.001 difference, then more number of reservoirs are there. That means we can conceive of infinite number of reservoirs with very small resolution with the temperature difference, and always keep the body to contact with the reservoir successively, so that heat transfer takes place under infinite small temperature difference. This way we can get a reversible heat transfer. Okay, reversible heating process. Because if you cool this thing, similarly you will pass through this infinite number of reservoirs successively from other direction, so that the surroundings will get the heat back from where it gave the heat earlier. That means from which reservoir it gave the heat. So it will get back. So therefore, you think over it and you will see that we can conceive a reversible heat transfer process. Similarly, a reversible expansion and compression process mechanical work done I have told earlier. So this is precisely the concept of reversible process, which can never be achieved in practice, theoretically reversible process, but it can be achieved in the limiting case, that is quasi-reversible process or quasi-static process, when the departure from thermodynamic equilibrium is extremely small and the dissipative effects also tends to zero, and the process is extremely slow, process through the number of equilibrium states. Now we will come to a very important theorem known as Carnot theorem, or sometimes people tell this is probably the most important corollary of the second law, and from which the other deductions take place to give birth to other corollaries. So this is what, let us see here, the Carnot's theorem or Carnot's principle. There are two statements separately, the Carnot's theorem or principle. The efficiency of an irreversible heat engine is always less than the efficiency of a reversible one. That means reversible heat engine operating between the same two reservoirs. Similarly, the efficiencies of all reversible heat engines operating between the same two reservoirs are the same. Again I am telling, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one, reversible heat engine operating between the same two reservoirs. And another one is that efficiencies of all reversible heat engines operating between the same two reservoirs are the same. Now let me prove this one. Okay? Let me prove this one. Let us consider a heat source at temperature T1. One is a reversible heat engine and another it takes heat. Let us consider it takes heat Q1R and rejects Q2R to a sink T2. Let us have a sink T2 and develops WR. Then we consider we have another heat engine which is not reversible. It takes heat Q1, give Q2, they are all different W. Now, by reversible heat engine we mean that heat engine, the working system, operates in a thermodynamic cycle. Now, thermodynamic cycle is composed of number of processes such that the initial state equals to the final state. And when all processes are reversible processes, that constitute a reversible cycle. And a heat engine which operates on a reversible cycle is known as reversible heat engine. And if any process of the thermodynamic cycle is irreversible, this is an irreversible heat engine. Now let us first consider that Q1R, to prove that is Q1. Why? Because this Q1R minus Q2R is WR from conservation of energy. Here also Q1 minus Q2 is W. That means heat added minus heat rejected is the work done. In this equation, two are independent, one is dependent. That means if Q1 and Q2 are fixed, W is fixed. So therefore, if two are independent, out of these two, any one we can choose as per our choice. So this is the logic for which we consider Q1R is Q1. So according to, this is eta for this heat engine and this is for reversal. According to Carnots, that eta R is greater than eta. But we first start with eta R and we will show this is not possible, is less than eta. Eta R is less than eta. Now what is eta R? Eta R is W1R divided by Q1. What is eta? Is W1 by Q1. Now if Q1 is same, Q1 and Q1R is same, Q1R is same, then if we have considered eta R is less than eta, then W1R is less than W1. W1R is less than W1. If we consider eta R is eta, just Carnots theorem, we don't accept. That means W1R is less than W. Then what we consider, then what we do, now here we just reverse this heat engine in the opposite direction. That means you can draw another figure that here I am doing like this. I have this opportunity to work as heat pump or refrigerator. Reverse. Now since this is a reversible heat engine operating on a reversible cycle, if we reverse all the processes, then surrounding will come to the initial state. That means it will resemble this same magnitude of the heat transfer but in the opposite direction. That means it will take Q2R heat from the sink and gives Q1R heat to the source, taking WR work. So the work requirement will be there for the heat pump, the direction is changed, it will be same. The heat will be pumped to the source but not taken from the source, then but the magnitude will be same. Similarly, heat will be taken from the sink, not rejected to the sink when it operates as a heat pump or refrigerator. Magnitude will be same because this is a reversible heat engine. This cannot be done like that. This can be made to operate in the reverse direction, but these quantities will be changed. Now, if we make this reversible heat engine or refrigerator as a reversible heat pump, reversible heat engine to a reversible heat pump or refrigerator, this will appear. Now since W1R is less than W, I link this and still I get W1R minus, W1 minus W1R amount of work. W1 is the work by this irreversible engine. That means since irreversible engine work is more than the reversible engine work, because we consider eta R is less than eta, eta greater than eta. So therefore this is less. So a part of the work is taken so that we get a net amount of work W1 minus W1. Now you see, since Q1R is Q1 we took, and this gives heat to this thermal reservoir or source, and from the same source as T1 it takes heat, there is no need of this T1, this reservoir. Why? Because simply we can eliminate the reservoir and can join these two. That means the working fluid at T1 will act as the sink where the heat will be given by the heat pump, and the working fluid here where from it will take heat will as the source for this heat engine. So therefore, since this Q1R is Q1 and they are taken from the same temperature, so they can be linked like this. So the working fluid of this will act as the source for this, and the working fluid of this act as the sink for this heat pump. That means what happens? The combined system violates the Kelvin Planck statement. That means it interacts with single fixed reservoir and develops a net amount of work W1 minus WR. This is not acceptable by the law of nature as the second law, which is Kelvin Planck statement. So therefore, eta R cannot be less than eta. So there are two opportunities, two possibilities: eta R is eta or eta R is greater than eta. Now how to get rid of this opportunity, this condition? There are two situations, there are two possible solutions. Eta R cannot be greater than eta because this violates the Kelvin Planck statement. So eta R cannot be less than eta, not greater, that is, this Kelvin Planck statement is violated. So therefore eta R is either eta or eta R is greater than eta. So if eta R is eta, then what happens? All the heat transfer and the work done will be same for the two engines. This is a logic only. There cannot be any analytical proof, because we consider the reversible and irreversible engine are different in terms of their performance. If eta is equal to eta R, and if we take QR is equal to Q1R is equal to Q1, earlier which I took in the another figure, that both heat engines are there, one reversible, another irreversible. If eta is eta, they will reject same heat and they will develop same work automatically. That means the performance will be identical in terms of heat and work interaction. That cannot happen. But this is the basic assumption, or this is the basic realization, that irreversible engine and reversible engine cannot interact with the surrounding with the same heat and work interaction so that their efficiencies will be equal. Otherwise, the irreversible engine will become a reversible one. So that logic puts that logic imposes the condition that it is not valid. That means reversible engine efficiency cannot be equal to the irreversible engine efficiency, or other irreversible engine efficiency cannot be equal to reversible engine efficiency. Otherwise, everything will be same, irreversible engine will be reversible engine, because the reversible cycle is characterized by its performance, that is efficient performance, no dissipation. So a cycle with dissipation, okay, the first processes with dissipation cannot reveal with the same efficiency. So this is not accepted. So therefore, the only solution is that eta R, that means the efficiency of a reversible engine is greater than the efficiency of an irreversible engine. So therefore, the first statement is proved that the efficiency of a reversible engine working between the same two temperature levels, that means same two thermal reservoir, source and sink, the reversible engine has a higher efficiency always than the irreversible engine. Next, we have to prove that efficiency of all reversible engines operating between the same source and sink are the same. That I will do in the next class. Thank you.